To finish up Chapter 5, we're going to be solving systems of linear inequalities. So we've got 3 warm-up problems. The first 2, you're just solving each inequality for y, meaning get y by itself. The third one, you are to graph the solutions of 4x plus 3y is greater than 9. Keep in mind, once you get y completely alone, we have to draw our boundary line based on our slope and our y-intercept. And then we need to determine, do we have a dashed boundary line or a solid boundary line, and do we shade above or below? So take a few minutes and complete your warm-up problems. Okay, so let's take a look at our solutions here. In the first one, we end up with y is less than negative 8x plus 6. Number 2, tricky part here, once we subtract 3x from both sides, we then have negative 2y is greater than negative 3x plus 10. Because we need to divide both sides by a negative 2, it means we need to flip our inequality symbol. So we have y is less than 3 halves x minus 5. And then in number 3, when we isolate y, we end up with y is greater than negative 4/3 x plus 3. The slope is negative 4/3. The y-intercept is positive 3. We need our boundary line to be a dashed line and shade above because it's greater than. So here's our y-intercept of 3, slope of 4, negative 4 over 3, negative 4 over 3. So our goal for today is to be able to graph and solve systems of linear inequalities in 2 variables. So we're combining our methods of solving systems of equations by graphing with solving or graphing a linear inequality. So a system of linear inequalities is a set of 2 or more linear inequalities containing 2 or more variables. A solution of a system of linear inequalities, well, that includes all of the ordered pairs that satisfy all of the linear inequalities in the system. So our solution is going to be a region. So the first couple examples, we're just asking to determine whether a given ordered pair is a solution to the system. So we have an xy, we have a system of linear inequalities. In order for our ordered pair, x comma y, to be a solution, we must be able to plug it into both of the inequalities and make both of them true. If it makes one or the other false, then it's not a solution. So upon substituting negative 1, negative 3 into the first linear inequality, we ended up with negative 3 is less than or equal to 4, which means, yep, that's good. Next, I plug in negative 1, negative 3 into the second linear inequality. Upon doing some PEMDAS, we end up with negative 3 is less than 0. Another true statement, therefore good. So because negative 1, negative 3 made both inequalities true, this is a solution. So first up, is the ordered pair negative 1, 5 a solution to our system of linear inequalities? So plugging into the first inequality, y, which is 5, oops, I don't want it that big. We've got y is less than negative 2x minus 1. So we're plugging in negative 1 and 5. So we've got 5 for y. Is it less than negative 2 times our x value of negative 1 minus 1? Well, when I PEMDAS on the right side, I've got negative 2 times negative 1, which gives me positive 2. So is 5 less than 2 minus 1? Well, 5 is not less than 1. So because the first linear inequality fails with this ordered pair, right away we know this is not a solution to the system. Okay, so it must make both true, otherwise it's not a solution. Let's take a look at number 2. Ordered pair we're checking is 0, 1. Here's our system of linear inequalities. Let's plug into the first one. Y, which is 1, is it less than negative 3 times x, which is 0 plus 2? Well, negative 3 times 0 is 0, so is 1 less than 2? Yeah. Okay, so it satisfies the first one. Let's check the second one. Inequality number 2 is y is greater than or equal to x minus 1, so plug in our x and y. So y, 1, is it greater than or equal to x, which is 0, minus 1? Well, yes, 1 is greater than or equal to negative 1. So because our ordered pair 0, 1 made both of these linear inequalities true, it means that our ordered pair 0, 1 is a solution. Okay, so you check out number 3. Is the ordered pair 0, 0 a solution to this system of linear inequalities? Well, hopefully pretty quickly you determined that 0, 0 is not a solution to this system of linear inequalities. It makes our first linear inequality false, so we don't even need to bother with the second one. All right, so let's take a look at, graphically speaking, how we can represent our solutions. So to show all the solutions of a system of linear inequalities, we need to graph the solutions for each linear inequality. The solution of the system, the solutions, there's going to be many, many, many. The solutions are represented by the overlapped shaded regions. So in example 1a, the linear inequality, the red one, dashed line shaded underneath. Then we've got our other linear inequality, the blue, that's solid shaded underneath. Well, where we have both regions shaded is right in here. Okay, so this particular now yellow region is our solution region because that's where I have both the red and the blue. Okay, and the blue, the boundary line, those ordered pairs would satisfy it. However, the dashed red boundary line, those ordered pairs would not satisfy the system. In example 1b, you'll see we've got the solid red line shaded above, the dashed blue line shaded below, and where we have both blue and reddish is this little sliver here. I don't know if I can make my highlighter small enough. Okay, you get the idea. So there is our solution region in that small piece. Ooh, I might be able to make it smaller. All right. So anything that is outside of this little solution region does not work, not a solution. All right, so let's take a look, and we're going to start graphing our own systems of linear inequalities. And it's also asking us to give 2 ordered pairs that are solutions and 2 ordered pairs that are not solutions to the system based on our graphs. So if I take a look at number 4, the first linear inequality says negative 3x plus 2y is greater than or equal to 2. So I want to put this in slope-intercept form. So I'm going to rewrite the linear inequality. And now I'm going to get y alone. So I'm going to add 3x to both sides, giving me 2y is greater than or equal to positive 3x plus 2. And then we get y completely alone by dividing both sides by 2. So that leaves us with y is greater than or equal to 3/2 x plus 1. The slope is 3/2. The y-intercept is 1. And based on the fact that this is greater than or equal to, it is a solid line shaded above. So let's get our plotting tools ready. y-intercept of 1, y-axis at 1, plot the point. Now we're going to rise 3, run 2. Rise 3, run 2. Could also go down 3, left 2. Down 3, left 2. Okay, so it is a solid line, so we can go ahead and I can use my nice little cheater line tool. Make that nice little line. Does continue on forever in both directions, so we need to include our arrows on the ends. We need to shade above our line, so here comes my shading in purple. Okay, and technically the points on the boundary line itself would satisfy this particular part of our system, or this particular part of our, this part of our system, which would be this one linear inequality. So because it's a solid line, anything on the line currently works. Now we need to bring in our linear inequality for the second inequality. So let's do that one in pink, and let's see how this overlapped region will end up working. So we've got y is less than 4x plus 3, so that's already ready to go in slope-intercept form. So our slope is 4 over 1. Our y-intercept is 3. Now, due to the fact that it is a less than, that means we have a dashed line and we're shading below. So if we get our plotting tools ready, we have a y-intercept of positive 3, so we go up 1, 2, 3, plot the point, and rise 4, run 1. Also go down 4, left 1, down 4, left 1, down 4, left 1. Okay, so all of my nice pink points are in a nice line. So I need to go ahead and try to make a dashed line through those points. So here it comes. Okay, arrows on the ends. And we are shading underneath. Okay, so getting our shading tools. Underneath where this y-intercept would be is actually kind of on this like right side of the pink line. So we're going to be all over here. And just be careful as we're close. You should hopefully see where the pink is now being drawn right over the purple to now determine where our solutions for the whole system occur. Okay, so if we look at the overlap shading, I zoom in. Left side here is purple only. Okay, so the purple only will satisfy only the first linear inequality. Down here on this far right, that is pink only. So ordered pairs in this region will satisfy only the second inequality. The white space satisfies neither. Where I have both the purple and the pink is within this sliver, where we've got the dashed pink boundary on the left and the solid purple boundary on the right. Okay, so let's do some coloring. All right, so I'm going to kind of label in here that this is a solution region. Okay, so we want to make sure that it's clear where our solution region is, because sometimes the coloring can get out of control. All right, so in order to answer the remainder of the question regarding where do we have two ordered pairs that are solutions and two that are not solutions, well, anything within this yellowish region is going to be a solution. So let's pick a couple points. Well, I'm going to go right 1, 2, 3, up 1, 2, 3, 4, 5, 6. So my ordered pair 3, 6 right here is in my shaded region. And let's go 4, 10. It's definitely in the overlapped region. Not solutions. Let's first go to the region where no solution for either occurs. So let's go down in here. So let's go negative 1, 2, 3, negative 1, 2, 3, 4. So negative 3, negative 4 is not a solution. And I'm going to pick 0, 0, my origin. It's only pink. It's not pink and purple. Okay, so 0, 0 only satisfies our second linear inequality. Let's take a look at number 5. This one's set up nicely. It's ready to go. I'm going to try some different colors, see how this works. So it says y is less than or equal to x plus 1. So for this particular inequality, my slope, and this is what I want to see from your work, I want to see the slope labeled. It's the invisible 1 before the x. The y-intercept is 1, because that's our b value. Because it's less than or equal to, it is a solid line shaded below. So if I get my plotting tools ready, it would be a good idea to use 2 different colors or 2 different types of pens, or a pen and a pencil. So if I start with my y-intercept of positive 1, slope of 1 over 1, rise 1, run 1, this one has a ton of nice plottable points. It's a little bit excessive, actually. But we'll keep it nice and consistent, go all the way through. Okay, down 1, left 1 also satisfies the slope of positive 1. And draw our solid line because of the or equal to. And we are shading below because it's less than or equal to. Okay, so I'll use my blue highlighter this time. Shade underneath the line, and again with this blue line, in terms of this part of our inequality, it does satisfy on the boundary for the blue. Let's go to the second inequality. That is y is greater than 2. Well, what kind of line is that? Remember, if it was just a y equals a number, that is going to be a horizontal line that slices through the y-axis at 2. Now that we've determined it's a horizontal line that crosses the y-axis at 2, we need to determine the type of shading. It's going to be a dashed line because it does not have the or equal to. So we've got dashed. And because it's y is greater than, we're going above. So I'm going to go straight to my graphing. Horizontal dashed line through y equals 2. Okay, so if we get our shading tools out, shading above that line, technically speaking, the boundary line itself does not work for this linear inequality due to the fact that it's dashed. And in terms of the system, what we're on the lookout for is where we have both the blue and green shaded regions, and that occurs right here in this little triangle. Okay, so the blue line, the boundary on the top leftish, those ordered pairs do satisfy the system, whereas the bottom boundary of the dashed green here does not. Okay, so here are our solutions. Now you give me two ordered pairs that are solutions and two ordered pairs that are not solutions to our system. So I gave two ordered pairs that are solutions. I gave the ordered pair 5, 3, and also the ordered pair 10, 7. Two ordered pairs that aren't solutions to the system would be -2, 1, and 1, 1. Okay, but you basically have a plethora of options for both scenarios here. Okay, taking a look at number 6. And number 6, our first linear inequality is y is greater than x minus 7. So this one we are in pretty good shape to start. It's in slope-intercept form. So if we have y is greater than x minus 7, that means our slope is the invisible 1 in front of the x, so 1 over 1. And our y-intercept, our b value, is -7. This is going to be a dashed line shaded above because it's y is greater than. If I get my second linear inequality set up, we need to get this in slope-intercept form. So I'm going to start by subtracting 3x from both sides, leaving me with 6y is less than or equal to -3x plus 12. We now need to divide both sides by 6, which gives us y is less than or equal to -1/2 x plus 2. So we need to simplify. We're now in slope-intercept form, where our slope is -1/2. And our y-intercept, our b value, is 2. Because we are less than or equal to, we have a solid line and shaded below. So I would like you to finish number 6 and identify two ordered pairs that are solutions to our system and two ordered pairs that are not solutions to the system. Okay, so you're set up for your first linear inequality, the blue one. You're set up with your second. You need to identify your solution region where we have both shading overlapping. Okay, and then pick two ordered pairs that are solutions and two that are not. All right, so hopefully this is what your graph looks like. So for our blue first linear inequality, y-intercept of -7, slope of +1, dashed line shaded above. Our second inequality, we had a y-intercept of +2, slope of -1/2, solid line shaded below. The two regions intersect in this large triangular region on kind of the left-hand side here. So two ordered pairs that I selected for solutions would be 0, 0 and -1, -1. Not solutions, 10, 0, and I also picked 5, 3.